Yeah, I don't remember. I don't wanna.
But I mean, it's fine. I think it's fine.
Okay.
Okay. Yeah. So hello everyone.
Yes.
Yeah.
Okay.
Today we have a pleasure to host Shubham.
Yes.
Shubham? Sorry. So he's recently graduated PhD student, and I mean this year he published quite a few really interesting papers in discrete diffusion, and today he will present one of his recent works on diffusion duality. With that being said, please take it away.
All right. Thank you. Thank you so much for the introduction. And yeah, so in today's talk, we're going to talk about the diffusion duality, which is probably my favorite paper out of all the papers that I've written in my PhD. Okay, so traditionally, autoregressive models have dominated language generation, but they now face serious competition from this new class of algorithms called diffusion language models. Unlike AR models, which generate text in a left-to-right fashion, diffusion models are non-autoregressive, meaning they're free from this constraint. Recently, these models have attracted significant attention, and with major releases such as Google's Gemini Diffusion and Inception Labs Mercury Coder and ByteDance's Seed Diffusion, right? Their impact has even reached the mainstream media, with Forbes and Fortune publishing articles that highlight the effectiveness of diffusion LMs. And all this excitement is justified. These models are not only highly effective, but also substantially faster than their autoregressive counterparts. Discrete diffusion is fairly new, and there are still a lot of open and interesting unanswered questions in this area. The first one is, well, we all know Gaussian diffusion models for text and video generation are far more mature. They support a rich set of techniques for efficient training and inference. In this paper, we ask, can we design a discrete diffusion framework that enables transfer of these advanced techniques from the continuous domain to the discrete domain? To answer this, we basically establish a connection between discrete diffusion and continuous state Gaussian diffusion, and we show that a specific kind of discrete diffusion process emerges from an underlying Gaussian diffusion. Now, the second question is, can discrete diffusion models support few step generation? So if you remember when in 2019, when Gaussian diffusion models became very popular, it took to generate an image, it would take thousands of steps, like somewhere between 1,000 to 10,000 steps. And in 6 years, these models are now supporting few step generation. That is, they can generate similar or even higher quality samples in probably 100x fewer steps, right? Now, in this work, we basically want to see if discrete diffusion models can also support such few step generation where let's say our goal is to generate 1,000 words. The question is, can we generate those 1,000 words in as few as 10 steps? Okay. We all know how an autoregressive model works. Just give me one. Okay, so you predict the first word, and then you predict the second word condition on the first word, so on and so forth. And as you keep on generating words, you ultimately end up generating the full sentence, as shown at the bottom. Naturally, to generate 11 words, you would require 11 steps of generation here. In contrast, there's this like specific this other kind of other kind of language generation paradigm, something called like the mass diffusion models. The way these models work is they start with a sequence of all blank tokens, and then you have a BERT-like model that selectively fills in the blanks. And as you keep on generating words in such a manner, as you can see, the first thing that you notice is words appear at random locations. And the second thing is you're predicting multiple words at one step, right? And you keep on doing this generation until you have filled all the blanks. And yeah, this is how your generation in mass diffusion models work. One thing as you can notice here is that you can get away with 7 steps of generation, let's say when you're generating 11 words, right? Again, the reason is you're predicting multiple words at the same time. Okay, now, we really want to do a few step generation, but one of the main challenges with mass diffusion models, as we see empirically, is that if you force these models to predict a lot of words at the same time, there's a degradation in quality. And one intuitive explanation for this is that in mass diffusion, if you notice here, once you predict a word, you cannot update the word because natively these models do not support this kind of generation style where you can like once you predict a word, it stays clean, and you're not allowed to flip words. And this basically follows from ancestral sampling. Like discrete diffusion models give you two things. One is a well-principled training loss or a bound in the likelihood. And the second is once you have trained a model, how do you sample from it, which is typically done using ancestral sampling. And ancestral sampling for mass diffusion models requires that you do not flip a predicted word. There are some heuristic methods which would heuristically wipe out some words, but once you do that, you're increasing the number of sampling steps, which pretty much goes against what we're trying to achieve here. Okay, there's a question from
yeah, so I have a question because can you maybe explain a little bit more on the concept of mask diffusion models, because I'm not that familiar, just to get a.
Oh,
yeah.
Oh, okay, perfect. Okay, so in mass diffusion, are you familiar with BERT?
A little bit. So yeah. So I'm not an expert on language models. So I just wanted to get a quick understanding of.
Yes. All right. So in autoregressive models, the way this works is, you have a transformer, and the transformer has causal attention, which says that during training, every word is solely conditioned on the previous word, right? Yeah. So you have a transformer with causal attention, and during inference, you predict a word, you feed that word into the transformer, which predicts the next word, so on and so forth, right? So to predict this word, the transformer takes this as the input, this sequence as the input, and predicts the next one. But in mass diffusion models, you have a transformer, but this transformer has bidirectional attention. That is, for instance, during training, the way you would train this model is you have a clean sentence shown at the bottom right. You would randomly wipe out some words and get an intermediate sample. For instance, let's say this one, right? Now you feed this into the transformer, which has bidirectional attention. That is, every word depends on every other word in the input, and you force the model to predict the missing words, right? And then there's a waiting term as well. But at a high level, your model sees a masked sequence, such as this one, and it is trained to reconstruct the missing words. That's it. There's nothing more fancy that goes on. And once you've trained the model now the question is, how do you sample from the model, right? Let's say you have trained this transformer. So the way sampling works is you start with all blank tokens and you feed this into the transformer. Then you randomly decide which positions to unmask or decode. Let's say at random, you decided, Earth, like the word at the second position and fifth position to be decoded, right? Once you've decided that, you just you ask the transformer, you just look at the likelihood of the model assigned for this blank, and then you sample from that categorical distribution. And that's how you sample. That's one sampling step, right? And then you recursively do this recursive update on the intermediate sample, and you end up with until you end up with a clean sentence, and that's your sampling process.
Can this be somehow similar to what is done in image domain in painting, or missing?
It is very similar to in painting. So in MDLM, right? Like, so this MDLM is currently used by ByteDance for their diffusion LLM. So the main contribution of this paper was to show that, like, people had been playing around with, just wiping out words. People had proposed a lot of like heuristic things, but they did not have a well-principled algorithm until our paper. Well, like there's D3PM that laid the foundational works for all kinds of discrete diffusion models. But the training loss proposed in D3PM, or the prior works, was very unstable. And the main contribution of this MDLM paper, right, this one over here, was to show that to propose a very simplified, a very simple training objective. And that simple training objective, it does a couple of things. The first thing is it is so simple that it doesn't incur any floating point issues. So until our paper, or said, I would say, or until 2024, to train a discrete diffusion model, you would need to use a very high precision, which cannot leverage the modern GPU architecture, right? Like you can only do float 64 training. It was only because the training objective was very unstable. But in this paper, we proposed a very simple training objective, which is a weighted cross entropy loss. And that simple training objective is also a bound on the log likelihood of the model. So to measure the quality of any LLM, we use a metric called perplexity. A lower perplexity means a better fit on the training data. Like this is a very hand-wavy explanation, right? So if you have a model with a lower perplexity, it means that it is learning it has captured the training data well. And because our training loss was mathematically the tightest possible bound on that perplexity, we got better numbers of we improved discrete diffusion models in that manner as well. Like one was stable train, we stabilized the training, so we had a better model. And on top of that, we measured the perplexity of the model using a more mathematically tighter bound, which led to improved performance of these models. So I hope I
just my last question. So this kind of like improvement on the loss from your 24 paper, was it besides the fact that maybe you provide a tighter bound to the log likelihood?
Part of the reason was, it was a tighter bound. Yeah.
Was it also somehow related to the way you mask for training to the masking or not?
Well, not so. So the improvements were because of two things. One was a stable training, because the likelihood bound that we proposed was mathematically the tightest, and also it was so simple to implement. Like the functional form of the equation was so simple to implement that it did not require any high precision training. It also reduced the training variance as well. Let me see if I can just quickly pull up. Okay, just a minute. New window. It is there on my website. Yes, I think I found it. PhD thesis.
But essentially, your new bound is just involve a new kind of weight, right? It's a tight, it's kind of like a better weighting at each time t that you guys
Not
did, right?
necessarily. It's about the weighting. But let me show you. I think it's here. Okay, so this is what I'm talking about. Like until to train, like D3PM proposed this bound on the likelihood, right? So as you can see, there's a summation term, which adds probably 50,000 numbers. Like the vocab size is typically in the range of tens of thousands. So you're adding 50,000 numbers, and computing each of those numbers is numerically unstable, because this is a PMF, and like to compute this PMF, it features division, and then it features division of even these unstable terms, QIs, right? So because of this reason, D3PM wasn't successful at all. And then Kim said, one of the baselines, again, that had this issue of higher variance. But what we propose is this weighted cross entropy loss. So, okay, to compute this objective at the top, you require addition over 50,000 terms. And then there's an addition over your sequence length as well, right? But what we propose is this. We show that mathematically it can reduce this using some linear algebra and taking a limit, that is formulating the diffusion process in a continuous time space. And when you do that, the discrete diffusion process, the discrete state Markovian process reduces to a continuous, discrete states continuous Markovian process. And you end up getting a very simple log likelihood. And this training loss is what made all the difference, has made all the difference.
Yeah, thanks. Yeah, great. Makes sense.
Okay, so now for a few step generation. Okay, so again, our goal is how can we perform few step generation in these models, and in mass diffusion models, because you cannot update a predicted word, you cannot perform few step generation because there's a catastrophic degradation in sample quality. So for those reasons, we're gonna take a look at this other kind of discrete diffusion process. It's called the uniform state discrete diffusion models. The way these models work is this. So you start with a sequence of all a randomly initialized token, and you train a transformer that updates word at each step. So the underlying words are the ones that are updated, right? And you recursively feed this sequence into the transformer, and then the transformer predicts the less noisier version of the noisy sequence. And yeah, and one thing if you notice, these kinds of diffusion models, right, or diffusion processes, they support they can update their predictions. Like here, the word plaza changes to moon, and then moon changes to earth, right? And because these models natively support this sort of iterative refinement of every token, these models are more suitable for few step generation. But historically, these models have been known to underperform mass diffusion models or autoregressive models. So that's why the people had written off this algorithm. People didn't see much value in USDMs until this paper. Okay, so what are the key contributions of this paper? Well, the first thing is that we're going to take a look at in the subsequent slides. Sorry, is there a question or?
I don't know. It was my impression that 100 times faster. Yes, it's great.
Yeah. And okay, yeah, and you know, like people keep on throwing such numbers where there is. Okay, I mean, I'd be very suspicious if I saw a claim like this, but also you have to understand that like such speedups have been seen in Gaussian diffusion models. So, like Gaussian diffusion models took 6 years to go from maybe to reduce the number of sampling steps from 1,000 to maybe 2 or 3, right? From 2019 till 2025. And in this paper, we basically compress the 6 years of research that was done for Gaussian diffusion in one paper, which is why I mean, yeah, if you're familiar with all the improvements that were made in Gaussian diffusion over 6 years, we were able to achieve that in a single paper in discrete diffusion because we could map the techniques. We could show that these discrete diffusion processes they have an underlying Gaussian diffusion process, and we basically exploit that relationship to get this kind of speed up. Okay, so for the remainder of the talk, I'll describe the method as to how this I'll try to give an intuitive explanation of this relationship between discrete diffusion and Gaussian diffusion. And after that, we'll talk about the technique, how to design a faster training curriculum for these discrete diffusion models. And next, we'll take a look at discrete consistency distillation that led to about like 2 orders of magnitude speed up. Okay, now what I'm showing you on this screen is a uniform state discrete diffusion process for a single token or cat. What we saw earlier was USDMs defined at the sequence level. Now, for simplicity, we're going to take a look at how, what are these discrete diffusion, or how is this discrete diffusion process defined for a single token, let's say the word cat, right? So in orange, or this is orange. Yeah. So in orange, what we have is a one-hot representation of that word. This is how you represent cat, how dog, and this is the horse, right? So in the for process, you start with a clean token, and the USDN, like the uniform state diffusion, will corrupt this clean data, right? And the way this corruption works is you assign some probability with which any word can transition to any other word. So naturally, you can see you start with the word cat, which eventually becomes dog, which eventually becomes horse, right? So Okay, now what we're going to do is define a function alpha t. Alpha t starts at equals 1, and it goes all the way to t equals, and it goes all the way to 0 at t equals 1. Alpha t equals 1 represents your clean data, which is the word cat, and alpha t equals 0 represents your garbage data, which is horse, right? The forward process in uniform state diffusion, it maps this one hot, this is the PMF representation of the word cat. It will transform this blue vector here to the blue vector here, which is a uniform distribution over all possible vocabulary, right? Let's say your vocabulary size is 4. And that's why you see, so this is what the uniform prior looks like. Now for the intermediate marginals, it's a linear combination of your clean data, like, alpha tx of this blue quantity here, and then this blue quantity here, which is here, right? So for the purposes of this talk, just keep in mind this intermediate marginal. This is the expression that is going to be most critical in understanding the relationship between the uniform state discrete diffusion and the Gaussian diffusion. All right. Okay. So so given that forward process, there's a very well-defined reverse process as well. So I'm just showing this equation for the sake of completeness. What this equation tells us is that given a noisy sample ZT, right? So let's say you're given ZT, and X theta is a denoising model with bidirectional attention, right? This equation defines a distribution over what possible tokens belong at the time step S. So you're given a noisy sample ZT, you feed this into a transformer X theta, which will define a distribution at this is a one hot representation, not one hot, sorry. This is a categorical probability distribution at time step S. Sorry, yeah, there's a question, I believe.
Yes, I just wanted to, like, for notation, these brackets, are they it's inner product or
inner product? Yeah.
Yeah, just yeah.
Oh, yeah. I mean, yeah, I should have clarified this. But yeah, I mean, the functional form is important. All this tells you is that given a noisy sample ZT and a transformer X theta, how do you retrieve a distribution at the less noisy time step S? So yeah. Okay. Now, well, that's a reverse process. Now, corresponding to the now the question is how do you even go about training the transformer that will take you from the time step t to s? For autoregressive models, we can compute the exact likelihood, which is the autoregressive factorization of a given sequence x. But for diffusion models, you cannot compute the exact likelihood. But what you can do is compute a bound in the likelihood, as you would do for any variational model. So the bound and the training loss is effectively this ugly equation here. Again, I'm showing this just for the sake of completeness. The exact form does not matter. The only takeaway here is that your x theta, so it assumes the minimum value when your approximate reconstruction of your input matches the true input. That's it, right? This loss forces the denoising model to predict the clean sentence X given a noisy sentence ZT. Okay. Okay, so now we understand, right, like how a discrete diffusion process is defined over at a token level. Yeah. So one other thing that what we can do is you can treat the one hot vector as real valued vector, and you can define a Gaussian diffusion process. The way that you define the forward process in Gaussian diffusion is you take this one hot vector and you simply add some Gaussian noise to it. So the intermediate marginal of this yellow vector is shown here, right? So it says, you have your clean data X, you scale it down by some quantity alpha T, and you add some Gaussian noise of this level, and your ZT tilde can look something like this. As you can see, like this number is highest because it sort of even though you start with this one hot vector, ZT tilde looks like this. There's not much to say here, and in the extreme case when at t equals 1, you'll see that at t equals 1, alpha t reduces to 0, and your prior is essentially a normal distribution over k categories, right? So this is an alternate way of defining a diffusion process for your input data cat. Now, there are like a lot of reasons why one would want to do this. Well, first of all, we know Gaussian diffusion is well studied. So why even bother with discrete diffusion when you could just get away with, like Gaussian diffusion models? Now, here's an interesting observation that we make. What we see here is that if you take this discrete latent and if you apply an argmax takes in a continuous valued vector, and it represents a one-hot vector with 1 denoting the index of maximum entry. So the one-hot vector representation, like argmax of this vector, is this one over here because 1.3 is the highest number. So you see a 1 here, right? So one thing you must notice here is that this argmax operation can convert a Gaussian latent into a discrete latent, right? Like that's the very first observation. Now, this begs this question, like, are uniform state diffusion and Gaussian diffusion fundamentally related? Is there any connection between this discrete diffusion process defined in the token space versus, like this Gaussian diffusion process defined with the on the one-hot vector, treating them as real valued vectors? Okay, so this is what we do. First, let's say you have an one-hot vector x, you define a Gaussian diffusion process. This is the intermediate marginal of WT, and this is the prior distribution. And if you take argmax, you retrieve this discretized latent, right? Like ZT is the one-hot representation of WT, and Z1 is that of W1. In the paper, what we show that is you can compute a closed form expression for the probability distribution of ZT. And that expression takes this formula here, right? So what are we looking at, right? So here you have a Gaussian distribution with k dimensions. Argmax transforms this k-dimensional Gaussian distribution into a categorical distribution over k categories, right? And if you notice, and this tau of alpha t tilde, right, is essentially a one to like it's just a scalar transformation of alpha t tilde. It takes this following form as shown at the bottom. Again, like you can literally compute, like, yeah, the way you get this formula is by using, I don't know, standard probability, where you have a distribution, you have a transformation of that distribution, and you can retrieve the closed form solution for the distribution of the discrete random variable ZT. And what you see is this, like it is a linear combination of the one-hot vector X and this prior distribution 1 over K over a capital K, right? And this intermediate marginal is the intermediate marginal of a uniform state discrete diffusion process, as we saw a couple of slides ago. And this is the first observation. What we observe is this argmax not only converts this real valued vector to a one-hot discrete vector, but also it converts the corresponding marginals of a Gaussian diffusion process to the marginals of a uniform state diffusion process. And furthermore, there are some interesting properties that this intermediate marginals possess. Like if you call it PT, it satisfies this ODE, which is a signature of a Markovian uniform state discrete diffusion process. And the other thing is, well, like as I mentioned before, all we care about is the true likelihood of the model, which unfortunately isn't possible for discrete diffusion models, but we have access to a bound in the likelihood. And in the paper, we also show that the likelihood bound of the Gaussian diffusion process is looser than the likelihood bound of the discrete diffusion process. So for these reasons, it just makes sense to operate in the discrete space. Like you want to train this transformer with, like latents from the uniform state discrete diffusion process. And also during sampling, you never want to use a Gaussian diffusion that was defined on the one-hot vector. Even though, as I mentioned before, again, like our motivation is to borrow techniques from Gaussian diffusion, but in this slide, I'm saying, like, even though Gaussian diffusion is really well studied for images, mathematically, it just doesn't work as well as the discrete diffusion for generating discrete data. Okay. Now, in the next few slides, we'll try to leverage this duality between uniform state discrete diffusion and Gaussian diffusion to see how we can design a faster training algorithm for this uniform state diffusion model, right? Okay, so during training, you sample a noisy sequence, like let's say the one shown at the bottom, and then you have the clean sequence at the top, right? So if you recall, we train this transformer using the diffusion elbow, which essentially forces this transformer to predict the clean words for the words that are corrupt. And for the clean, for the corrupt words, the transformer is forced to predict the clean words, and the words that are clean, the transformer is forced to copy over these words. And so this is the corresponding one-hot representation of those words, right? But if you remember from the previous slides, we showed that this one-hot discrete vector is essentially an argmax of a Gaussian latent, which is sampled from, like a real valued vector x, and then and you add Gaussian noise to it, to the real valued vector x. What we do in the paper is we basically say, instead of doing the argmax, if you take a softmax of this vector, with a temperature tau, and you feed this into the model, the task of denoising becomes easier. And the intuition is this, right? I mean, earlier, if you remember, you had a one-hot noisy vector, which was which had no, the problem with discrete noise is that it's a hard transition. Like, you have a clean word cat, and it transitions all the way to a corrupt word, let's say bat, right? There is no intermediate, there's no notion of gradual change as one sees in Gaussian diffusion or diffusion processes defined on continuous real value data, right? But here, if you see, when you take the softmax of this vector, it's a superposition of the clean word cat and also the noisy word bat, right? So that's why there is some signal retained, and there's more signal retained in the softmax vector than it was in the case of this hard argmax. There was so because of these reasons, when you train the model with this soft latents, and we observe improved training. We'll take a look at the results later. Now, the most important question is, how do you even design these transformers, right? The way transformers work is they receive a sequence of discrete inputs that would perform a vocab, like an embedding lookup based on those discrete input, and then they would perform a forward pass. But here, because you have a continuous valued vector, the way we implement this is by performing a soft lookup where you have this vector sums up to 1. So you perform a matmul of this vector with the embedding matrix that gives you a weighted average of all possible words in the vocabulary, and you do the normal training. Yes, I guess there's a question.
Yeah, thanks. My question is about, because you mentioned that the Rmax was basically to kind of transform from the continuous space to the discrete space, right? And this softmax, I'm just trying to make sense how you use this softmax for training, because you...
Oh, yeah. So we approximate argmax. So argmax is essentially a softmax with temperature tau equals, in the limiting case of tau equals 0, right? So that's when the softmax reduces to argmax. But in the paper, we propose a very heuristic way of training these models, where we say that instead of setting tau to 0, which would be argmax, you set tau to some non-zero number. And the intuition is this. This way of training the model is easier for the transformer. It's easier for the transformer to reconstruct the clean sentence X, because your input to the model is a superposition of the clean and the noisy sequence. So here, for this word, which is incorrect, right? Earlier, the model was trying to reconstruct cat from bat, but now it's trying to reconstruct cat from this superposition of cat and bat.
Okay.
So there is this there is more signal in the input now than it was earlier. So this is the intuition as to like why training the model on this soft latents helps.
What I'm a bit confused is because I thought you were mentioning that it's better to train in discrete.
Yes,
time?
we will come to that. Yes, yes. I think
okay.
yes, yeah.
Yeah. So my confusion is mostly the fact that okay, you kind of like link this continuous with discrete via the R max. Yeah. Or I guess you will explain that later. Right?
Yes, yes. I think that's a great question. So in the in the earlier slides, I said you should always be okay. The reason why I said you should always train your model in the discrete space is because of the bound and the likelihood, right? Here, what we do is we train the model. We're training the model with this elbow formulation, which is defined in the discrete space, but the input to the model is in continuous space. So you see, like this is like so this no longer again, this is a very heuristic way of training the model. You do not have like discrete elbow is defined for discrete inputs. Continuous elbow is defined for continuous inputs. So if you mix and match things where the input to the model is in continuous space and your elbow is defined in the discrete space, you no longer have a valid elbow, right? So to evaluate the model, you always evaluate it as a discrete diffusion model, but it's only during training you do this thing, right? So, okay. So one thing, so this is the training objective, and this function, this f is something that we saw earlier. The form doesn't matter. What we see here is this, right? Like all we have done is replace the input to the denoising transformer. Instead of having argmax, we have a softmax over temperature temp. And once you replace the softmax with argmax, you retrieve the true training elbow because your input is discrete, your elbow is defined in the discrete space. But when it's softmax, it is no longer a valid elbow. And we do this curriculum tau, right? Like what we observe is when you like in the initial, okay, we set a non-zero value for tau in the initial stages of training, and for the remaining stages, we just replace tau to with zero, which is essentially an argmax. So you only do this curriculum learning in the initial stages of the training, and it introduces a bias, but it lowers the training variance. And then for the remainder of the training, you just train as a discrete diffusion models, and it leads to improved numbers, as we'll see in the next few slides. And the main reason, like, okay, you do this funky thing. Now the question is, why does it work? We have some intuition as to why, because it's your input to the model is a superposition of your noisy token and your clean token as well. So that's why it's easier for the denoising model to decode to reconstruct the clean signal X. The other reason is, and this also manifests in a lower training variance of the gradients. So if you were to, so on the y-axis, we have the variance of the gradients across the top 100 weights with highest variance in the entire transformer, right? So what we see is, on the x-axis, you have training steps. So what we see is Duo without curriculum learning has a higher training variance for a subset of the weights than it is for, Duo with curriculum learning. So because, with curriculum learning, you have lowered gradient variance, it leads to more stable training of these models. So this is, so this is the curriculum learning.
And the variance of the gradients is per batch, right? Not for the whole chain.
For a given mini batch of for a given batch of sentences, and also this is not the sum or the average of all the gradients. This is the sum of the top 100 weights with the highest gradient variance. Because that's where we saw the biggest gap in variance. If you were to analyze the sum of all the average variance across all the weights, there's still difference, but it's not as prominent as this one. So
just one question. So the motivation from this was mostly based from the intuition that you kind of want to help a little bit the transformer to get this kind of like smoothness between the transition from the clean signal to a noisier signal at
Yes,
early stage.
yes,
And
yeah. Go ahead.
oh, yeah, no, so I was trying to understand if this was coming more from an intuitive perspective or there is
Yes.
like a theoretical understanding of why, and also just to understand if this was due to the fact that you mentioned that you're using a transformer, right? So the transformer needs to kind of help himself a little bit more into
Yes.
what is this kind of transition from a clean signal to a noisier signal?
Yeah. Yeah. I think. So what I observed initially was that what I initially wanted to do was to define an elbow for in the discrete space, but have your Gaussian latents in the have your input to the denoising model in the continuous space, and come up with an elbow for this hybrid process. But it was not possible. But while I was running experiments, it was more empirical when I saw that once your input to the transformer is in the continuous space, you see a drop in loss. And once I saw that, I was like, okay, so now I can literally compare the magnitude of this, the discreteness in the input. And I can definitely control the loss in a way it doesn't deviate too much from the true discrete diffusion loss, while also being lower. So the moment I saw a loss that was lower than your standard discrete diffusion loss, I knew like there was a way to control it and get more, just like reduce variance. It was more empirical than anything. So
Yeah, that's pretty nice.
yeah. I mean, yeah, it was.
Yeah.
I mean, I mean, my main motivation was to design the distillation, and it was something on the side basically, but it's pretty impactful regardless.
But
Okay.
you would say that this is because of the use of the transformer. So maybe if you change it to a different architecture, you need to analyze kind of like this behavior.
I would no, but I think the intuition should also hold where the intuition here is that because it's superposition of the clean and the corrupt token, there's more information in the input than the input for in the pure discrete diffusion case, right? Because there's more information, the loss has to drop regardless of your choice of the denoising model. And for those reasons, because it's an easier task, you can regulate the easiness of the task and make it harder gradually, which will give you a curriculum. So
yeah, thanks.
now when we look at now I'm showing some likelihood evaluation numbers on language modeling tasks. We used open web text. All our transformers were trained for 1 million steps with a context length of 1024. On the y-axis, we have perplexity. So a lower number is better. A lower number means a higher quality model. Okay, so in black, we have autoregressive models. In red, we have MDLM, which is a mass diffusion model. And our main baselines are the state-of-the-art uniform state discrete diffusion models, right? Like SED and UDLM. And we see that Duo, our method, gets better perplexity than the previous discrete diffusion models, while approaching the perplexity of the mass diffusion models. Now we check the out-of-data generalization capabilities of Duo. What we see is if you take a trained model on open web text and you evaluate how well the model fits these other data sets, right, like PTB, Wikitext, or LM1B, we see that on 3 out of 7 tasks, Duo gets a better likelihood number than AR, which is pretty significant because until this paper, everybody thought uniform state discrete diffusion models were strictly worse than mass diffusion models. But here, at least now, because of this curriculum learning strategy, we were able to show that these can be as competitive as AR models, at least on downstream tasks, which is what you care about anyway. Okay, now the second part of the talk is about faster inference. For Gaussian diffusion models, all the distillation algorithms, they require something called PFOD. So this equation is a deterministic mapping from your Gaussian noise to the clean data, right? So all the samplers that we talked about before, the ancestral sampler, especially for the discrete diffusion models, is stochastic, meaning you have a noisy sample ZT. That noisy sample ZT will give you a distribution over all possible tokens in ZS, right? Which is a less noisy sample. But in Gaussian diffusion, you have many different kinds of samplers. In many cases, it doesn't really have to be stochastic all the time. There are deterministic equations that take you from noise to clean data. We'll see an example in the next slide. So all the distillation algorithms require the existence of PFODs, which are non-existent for discrete diffusion models. At least no paper has been able to show that these deterministic transformation exist for discrete diffusion models. And one example of PFOD, like this is what a PFOD essentially looks like. Like if you look at this, it is an interpolation of your alpha T tilde, your clean data X and your Gaussian noise W1, and it's a deterministic transformation of these two, right? Okay, now what we're going to do is we're going to leverage this PFOD, which is defined in the Gaussian space, to construct a distillation algorithm in the discrete space. So in consistency distillation, the way this works is you sample a time step t and a time step s. S is always less than t. Corresponding to these time steps, you take the argmax of these continuous valued vectors, right, to get zs and zt. You have a student model, and then you also have a teacher model. So in distillation, you initialize both the student and the teachers with the same transfer. Like let's say you have a pre-trained model. You take a pre-trained model, you initialize the student and the transformer with the same weights. The only difference now is that during distillation, you freeze the weights of these teacher models, but you only update the weights of the student model. Now the student model sees a noisier version of the input ZT, and the teacher model always sees a less noisier version of your input X. And you're always forcing the student model to match the predictions of the teacher model, which sees a less noisier version, right? You can already see it, right? Like if S is equal to 0, you're forcing the student model to predict the clean sentence X in just one step, or like in just one step from T. So yeah, this is distillation in a nutshell. To reiterate, you have a student model that sees a noisy sequence ZT. You have a teacher model that sees a less noisy sequence ZS, and then you train the student model to match the predictions of the teacher model by optimizing this loss here. As I mentioned before, distillation proceeds in numerous rounds. Let's say you, in your first round of distillation, you use a step size of delta. You sample numerous SNTs, and you perform numerous gradient updates in the student model. And once you train the student model, and once you distill the student model for one round, you move on to the next round, where you increase the step size by a factor of 2. And you repeat the process again. And then after every round of distillation, the student becomes the teacher for the next round during initialization. And then you always update the student model while freezing the weights of the teacher model during distillation. And so the distillation now proceeds in multiple rounds, and you can already see, right, like in the very limiting case, you're forcing the student model to predict the clean sentence X in just one step. So this is the key to few step generation in discrete diffusion models. Now, again, the consistency distillation was proposed, was proposed for images and everything, but the only reason people weren't able to use this algorithm for the distillation of discrete diffusion models was only because this connection between this continuous and discrete was missing. Now, this loss that I showed you before was for a single token. You can easily extend it to at a sequence level, where you are computing the KL at every index across the entire sequence. And now, about the results, right? On the y-axis, we have generative perplexity. So this is a metric which requires samples from, it just requires some samples. It can be from an autoregressive model, from a discrete diffusion model. And then if we feed those, can evaluate the likelihood of those samples under a different teacher AR model, which is of much bigger size. And so naturally, you know, like a lower number means higher quality samples. And on the x-axis, we have the number of sampling steps. Again, like the ideal area, so the most desirable area is this one over here, which means low sampling steps and high quality samples, right? Okay, we have MDLM in orange, we have MDL, and then Duo. Our method is called Duo. So our method is in dotted blue. What we already observe is that Duo gets better sample quality than MDLM, but there's a slight degradation in sample diversity. So in brackets, I'm also denoting sample diversity. This is the base model. So now, if you distill MDLM using an algorithm called SDTT, and you distilled Duo using our method, you get this blue curve here. What we observe is that when the number of sampling steps is high, MDLM gets a better sample quality than Duo model, but in the low sampling steps regime, which is what we're interested in anyway, our method gets much better sample quality than the MDLM model, especially at t equals 8 and 16 sampling steps, right? And in the paper, we also propose a greedy sampler, which is analogous to nucleus sampling in AR models. And when you do that, the sample quality improves even further. Here you see that Duo almost matches the sample quality of an AR model and also an MDLM model at the cost of a reduced diversity. Like Duo produces like less diverse samples, and that's how it gets better quality samples. But in the low sampling steps regime, it's just like significantly better than MDLM. So yeah. Now, in this slide, I want to show how effective was the distillation algorithm, right? So in gray, you have the Duo model with 1024 sampling steps, and y-axis is generative perplexity. You see that after you distill the model over 5 steps, you get almost similar quality samples, which is measured by GenPPL, and no degradation in entropy. So you get about 50x speed up without sacrificing any diversity with the distillation algorithm that we proposed. And then if you go to even fewer sampling steps, right? Like if you want to generate 1,000 tokens in just 8 steps, you might want to use our greedy tail sampler, which essentially it's just like a greedy decoding scheme, which where we want to sacrifice sample diversity for improved sample quality. And when you use our greedy tail sampler with the Duo model, you see that the sample quality is slightly better than the base model, but there's a degradation in sample diversity, a slight degradation in sample diversity. So sorry, there's a question, I believe, or?
Yes. So you said that perplexity we want it to be as low as possible, right?
Yeah.
Then I mean here this still looks like has lower perplexity if I'm reading this correctly.
Yes. So so now the question is, why does the distilled model get a better perplexity than the base model, right? How can your distilled model, how can the student be better than teacher? The answer is from this reduced diversity. So basically, while distillation, as you decrease the number of sampling steps, the model learns to capture a few interesting modes of the data. Imagine you have a bimodal or multimodal distribution, right? The model just generate samples from those specific nodes. Like that's the intuitive explanation. So you produce less diverse samples, which also means that the sample quality for that subset of the samples is higher. So yeah.
Is that somehow connected to maybe you are like increasing memorization with distillation or?
Memorization, I don't know if we can comment on memorization, but definitely like so let's say your base model generates samples from many different topics like math, science, English, whatever, right? But maybe in the distributed model, you only see examples from maths and science, and not from other topics. And because you know, in the low sampling steps regime, you only generate samples from those particular topics, and those samples happen, and those samples are also like of higher quality than, you know, well, yeah, it's just a way to like not game, but like it's a way. It's definitely not a bug. It's more of a feature, because in Gaussian diffusion models as well, it is very desirable to reduce the diversity at the expense of sample quality. So that's what you achieve here. But yeah, it's I don't think it's related to memorization, or if it can be related to memorization. It's at the top of my head. So yeah.
Regarding distillation again, there's always a second term that kind of help corrects as well, right? Is that it's not just a lost involvement of the teacher and student, it's also another term that involves the training data.
Oh, no, we would not use, sure, like, I think it's worth
okay.
exploring. So what you could do is add a regularized loss that predicts the clean data X from ZT. We did not play around with any funky, I can totally see it improving though.
I see.
Um,
Oh, that's interesting. So you guys didn't use that, and it still worked
yeah,
pretty well.
Yeah. I think my main motivation was to stay as close to the consistency distillation as defined for Gaussian diffusion models. For those
Right.
reasons, I didn't want to like play around. Yeah, I just didn't want to give off the impression that this method is more contrived or it requires additional engineering. So yeah, so
Yeah.
I never played around. I never played around with those losses.
Yeah. No worries. That's quite interesting actually.
Yeah. Um, Yeah, and then so now we have some follow-up work as well. I'll just like spend one slide talking about it. So we have a follow-up of this diffusion duality series in the diffusion duality. So in this subsequent paper, we propose something called psi samplers, which is a predictor corrector sampler. And what you observe is this, right? Like on language generation, especially with predicted corrector methods. So in the previous slides, we only talked about ancestral sampling, where for mass diffusion, if you predict a word, you cannot update the word, right? But if you apply some remasking, then the sample quality improves, but but you also increase the number of sampling steps. So there were no such equivalent. The equivalent to remasking and mass diffusion, there was no such equivalent for uniform state diffusion. So we proposed some interesting samplers which leverages this duality, and we were able to show that the sample quality improves from like this is the base model, right? So the performance of the base model improves from this to this solid blue line here. So this is yeah, this is one set of results and on image generation where you desire more FID, we clearly see that Duo with this improved sampler that we proposed gets better quality samples than MDLM, which is again like pretty astonishing because until this paper, uniform state diffusion was strictly worse than mass diffusion and also autoregressive models. But in this paper, we were able to show that these models can be made competitive with AR models, as we saw in zero-shot likelihood benchmarks. And also here, like these models are strictly better in the low sampling steps regime here for language generation. And even for image generation, they are strictly better than mass diffusion models. And for image generation, especially like we know Gaussian diffusion works really well. And given how similar uniform state is to Gaussian diffusion, this is the kind of behavior that one can expect. But nevertheless, until this paper, we didn't really have such results. So yeah. Okay, so in conclusion, we saw how we drew a connection between uniform state diffusion and Gaussian diffusion in the continuous space, and we showed how this duality can be used to improve the training of uniform state diffusion models, where we achieved 2x faster training. And we also saw how we can map techniques, a lot of existing techniques from Gaussian diffusion to uniform state diffusion. One prominent example being consistency distillation, which led to about like 100x faster sampling. So yeah, I think that's about it. That's the end of my talk.
Thank you. So we should thank you.
Thank you. Yeah.
Thank you for joining. I'm sorry I couldn't follow the beginning of the talk.
No worries, it happens. So yeah.
But now we have time for discussion. Does anyone have any questions? Maybe Ingo, because like you need to go, so maybe if you have a question, you can.
Thank you. Yeah. So I just have a question in general. If you go from the argmax case again to a softmax case to have a better or to have a smoothing between these functions, do you see that these discrete diffusion models could also use things like sampling techniques, top P, top K samplings that improve the inference and generation quality pretty significantly in autoregressive models?
100%. I think we did something similar for mass diffusion. I mean, in this paper. I'm not sure if you are familiar, like remasking again, like it was from my lab at Cornell. And in the paper, we basically see the same thing where if you have some top K or temperature sampling, it does improve the sample quality. But in practice, well, it improves the sample quality of mass diffusion models, but it does not improve the sample quality of the uniform state diffusion models. And we will be putting this paper up on archive like in 2 weeks or so, and we do have some ablations. So this like Diffusion Duality Chapter 2 is all about the samplers and improved curriculum learning of this model. So in short, it helps mass diffusion, but it does not help uniform state diffusion.
Okay, very interesting.
Yeah. But temperature scaling is something that helps both, but top K or top P only helps mass.
Okay, that's interesting.
Yeah.
Also, one follow-up question. Do you think, or how does the perplexity vary? Have you run any experiments between if you go to longer context lengths and the 1024 that you mentioned? Do you think that the discrete diffusion models are able to scale to these context lengths, or do they drop off at some point? Do you have any experience there?
Yeah. So when we were working on this MDLM paper, right, like this mass diffusion language model paper, in that paper, we tried context lengths up to 10,000, but we did not see any improvements. Like we did not see any improvements in case of mass diffusion relative to AR. Like the gap was still similar. But what I truly believe is like at longer contexts, you should see better sample quality with diffusion because again, like bidirectional is much more expressive. But I don't know if diffusion will surpass AR by solely increasing the context length. What we have seen is if you restrict the number of unique tokens in your training data, let's say you restrict yourself to 1 billion or 10 billion tokens, with multiple epochs of training, diffusion just keeps on improving and it surpasses AR if you fix the number of unique tokens. But when you have infinite data, AR is strictly better than diffusion in terms of perplexity. But yeah, I
did not
know.
expect that. That's very interesting.
Oh yeah, no. So there are like at least 2 works that establish this, that diffusion beat AR. I can share this paper. Diffusion beat AR. Yes, this paper. So for scaling laws, you assume you have infinite data. And when you have infinite data, like AR is just more compute efficient. Like if you have infinite data but fixed training compute, you would train an AR model. But diffusion is more data efficient, where let's say you have finite training data. Let's say let's say for some obscure language, maybe, I don't know, maybe German or something, where you probably have 10 billion unique tokens, right?
Yeah.
So you would want to use a discrete diffusion model because you'll simply get better perplexity with a discrete diffusion model than with an AR model. And yeah, this is the paper basically. So
okay, well, thank you very much. Thank you. This was very interesting.
of course, yeah.